Welcome everyone to the 33rd Brazilian Mathematics Colloquium and to the introductory course on differential equation models in epidemiology. In this course, we will introduce differential equation models of infective diseases, which are diseases passed from person to person, such as COVID-19. In this course, you will learn about the modern theory of ordinary differential equations, including phase portraits, linearization, and slow-fast systems, and also the use of game theory to model the response of people to epidemics and vaccination programs. We will start with a simple model called the SIS model. In epidemiology, the population is assigned to compartments or subgroups with labels which usually show the flow patterns between the compartments. For this model, we will have two compartments, the susceptible and the infected. Some infections, for example, those from common cold and influenza, do not give immunity to the individuals upon recovery from the infection, and these individuals become susceptible again. We can represent this model by a single differential equation given certain relations between the susceptible and the infected. We will analyze the constants beta and gamma, which will help us determine the value of R naught, which is the basic reproduction number. This number indicates how many people will be infected from a single person who has a disease. We will study the points of equilibrium and the phase portrait of this equation, and then we also will be able to sketch some solutions for it. Sometimes certain diseases are better modeled using more compartments due to its nature. We will continue with the SIR model, which includes new compartment called removed. This compartment has individuals of the population who have been infected and then removed from the disease either due to immunization or due to death. Initially, it can be assumed that these individuals cannot be infected again or transmit the infection to others. In this case, we will use two differential equations to represent this model. It is not possible to integrate directly and obtain a solution, but we can analyze the phase portrait of the system. If we choose, we can analyze the case where the removed can become susceptible again. This means that those who have survived have lost their immunity. This also can be presented by a system of two differential equations, and as before, we will study their phase portrait and we will analyze the type of equilibria of this system. We could also study the case where an individual has been exposed to the disease and later becomes infectious. This could be the case where there is an incubation period of the disease. There are many ways to choose the compartments for these models. We could have, for example, different age groups or groups with pre-existing medical conditions. It depends on what we choose to study. In this course, we will use this model to study COVID-19, where this will be represented by 6 equations. This model, it is very difficult to study the phase portrait of the system, but we can study its equilibria. The equilibria will appear in a manifold of a certain codimension. We will see that transversally this manifold, there are a stable and unstable manifold. In a certain way, this behavior is similar to the hyperbolic behavior observed before, even though they're not. To study this behavior, we will have to analyze a 6x6 matrix, especially a 4x4 block that will give an idea of how the disease evolves. Now, there's an important question that arises on this case. How do we calculate R0? For this case, this calculation is far from simple, and we will try to answer this during our course. Most of the models studied up to now haven't been able to accurately represent the evolution of a disease. This is due to the fact that a very important factor was not included in them, and that is the human behavior. In this course, we will study a model which involves human behavior. We will see that this model represents more accurately the evolution of previous pandemics, such as the Spanish flu, and what we're observing in the present COVID-19 pandemic. We hope that this brief overview entices you to participate in the Brazilian Mathematics Colloquium and in our course. Thank you very much and wish to see you soon.